Welcome out, ladies and gentlemen, for another great night. I know we're doing a little different today because usually you're used to your Thursday lunches, but hey, we had someone special in town, so we wanted to give you all a special treat. All right, but before we get started, let me move my big head out the way, and I want to say thank you to. I don't know what a sponsor slide. Usually there's a sponsor slide. All right, did we get a slide today with the sponsors? Okay, yes.
Hey.
So here we go. We would like to thank our sponsors for this awesome food, you know. Yep, Merkle. Yes. Loving it. All right.
Just cross off all the other ones.
Before I get started, are we going to do the regular? Does anyone have any community announcements? Anna, come on, Greg. Come and get that spiel. Come on. All right.
Hey, I'm Anna Sherman. I'm the organizer for Codex X, and we have an event tomorrow night, which is adding users and authentication in Ruby on Rails. You don't have to know any of that stuff to come. It's open to everyone. We are the Women's Tech Group. It's just a place for people to feel empowered and learning to code. And so everyone's welcome. We're on meetups. That's at 6:30 tomorrow night. There's also Gig City Elixir, which is October 26th and 27th, or 27th, 28th. It's on the internets, which is a functional programming conference, and you guys should all check it out. I think that's it.
Thank you so much. Yes. All right, well, without further ado, we're going to welcome our friend Erin up to the stage, and he's going to give us an awesome talk. Right this way, my friend.
It's gonna be awesome. Hello, Chattanooga. So I'm going to give a talk about sponsors. JK. Okay, quick show of hands. Oh, I am loud. How many of you know what a Merkle tree is already? How many of you used a Merkle tree at your job or something like that? All right, I was just trying to gauge how hard-hitting your questions are going to be, and I feel very, very confident now that I can bamboozle all of you. All right, so I'm going to be talking about Merkle trees. A little bit about me. I work at Carbon 5 in Los Angeles. Carbon 5 is a company that will exchange dollars for programming services. So I work on a P2P project for a company called Protocol Labs. Carbon 5 is renting me out to them. And a Merkle tree is a data structure that we've used extensively on this project, which I didn't even know about before I started working for Protocol Labs. So a little bit about me. Let's talk about this guy, this handsome devil, Ralph Merkle. Ralph Merkle, from whom the Merkle tree name originates, is a computer scientist. He invented cryptographic hashing and co-invented public key encryption. So this guy is behind a bunch of the technologies that you probably already use today if you're not in the crypto space, and definitely use today if you are. He invented and patented the Merkle hash tree in 1979, but that patent expired in 2002, so you're seeing this data structure used in a bunch of different P2P projects. So a little calibration of terms. What I mean when I say cryptographic hash is a one-way collision-resistant function, which maps an arbitrary number of bytes to a fixed length bit array. So when I say collision-resistant, what I mean is that it's difficult, in most cases impossible, to find two inputs which will map to the same output. And it's one way, and that given some output from one of these functions, it's going to be very difficult, if not impossible, to compute the inputs. So talking about hashes, we use these things all the time. You're using them in Ruby. You're using them in shell programming. SHA-1, MD5, all these digests that you already use. Not rocket science. You're already familiar with these things. So we're going to use SHA-256 in this presentation. So without further ado, we're going to get into the Merkle tree stuff. So when I'm talking about a Merkle tree, what I mean is a tree structure in which all the leaves are hashes of some data, and then all non-leaves are hashes of their children's hashes. In building one of these things, we'll take a file, 8-byte file, duval.txt, ones and zeros. We'll chunk it up into 4 blocks. We're going to hash those blocks using our magic hashing function to produce some checksums. Then we're going to concatenate pairs of checksums hash those things, so on and so forth until we get down to a Merkle root. In the event that we do not have enough leaves to have a perfectly balanced tree, there are some strategies that we can employ to ensure that it feels like a balanced tree. So this is the method that Bitcoin uses to ensure perfectly balanced binary trees. It's just going to duplicate a leaf hash until we're able to balance all the way down to the root hash. So it's a data structure. Why use them? Some cool properties of Merkle trees. One, they're immutable. So in this particular example, if I change all these blue bits, then the hash has changed all the way down to the root, and I actually have a new tree. Given a root hash, assuming your implementation is not garbage, you can be sure that no one has tampered with your tree. This is also amenable to structural sharing. In as much as I have two trees with a leaf that's different, I can share between two different versions of the tree, subtrees, which is kind of a nice property. Small inclusion proof. So this is a feature that is useful for situations in which you need to prove that a leaf exists in the tree, and that proof needs to be transmitted over some network. And that transmission is somewhat expensive. So, for instance, I've got this 16-leaf tree here, and I, as the challenger, need to prove that the leaf with hash 77AC is in this big old tree. In this particular case, I need the sibling hash, which hashes to 0101. I need the uncle hash, F8AA, and I need the AB33 hash, and that's it. So just these this, and that, four hashes is all it is required to prove that one of these leaves exists in this 31-node tree. These things are tunable, so all the examples I'm going to be talking about are balanced Merkle trees with a branching factor of 2, but you can choose a different branching factor depending on your needs. So in this particular case, we choose the branching factor to be 4, and then we end up with a tree that is comprised of 21 hashes, but we trade off in proof size. So it's going to take 6 hashes, 1, 2, 3, 4, 5, 6, to prove that 77AC exists in this tree, as opposed to just 4. So real-world uses, I found out this Merkle tree existed, this data structure existed because of work that I was doing in protocol labs. And I set out, because I was hearing on the interwebs that Merkle tree is used, for instance, as part of Git and Cassandra. So I sat out and I tried to find some examples of where this thing is actually being applied. One of the ways that people use Merkle trees is in the Cassandra DB repair protocol. They use a Merkle tree to synchronize replicas in a cluster, or synchronize replica state in a cluster. So any of you use Cassandra, like your day job? No? Perfect for bamboozling. I love it. OK, so our Cassandra cluster is going to be organized. The nodes in this cluster are organized in a ring. And depending on your replication factor, data from one node in the cluster will be replicated clockwise on the ring to other instances acting as replicas. So in this particular situation, this guy owns tokens 0 through 40, and it'll replicate, because n equals 2, down to the next 2 nodes in the ring. Periodically, the repair protocol can be initiated, and one of the nodes in the cluster will act as a coordinator to ensure that all of the nodes in the replica set have the same data and will actually coordinate like a repair to ensure that they get into the same state. What this looks like is the node acting as repair coordinator will ask each replica to create a Merkle tree and send the Merkle hash where the Merkle tree is built over the data that replica is responsible for. So in this particular situation, we hash the data, we hash that all the way down to the Merkle root, and then the Merkle roots are all transmitted back to the replica coordinator. In this particular situation, because of the way that we've configured our Cassandra DB consensus, we have a quorum. So 2 of the 3 nodes think that the root for this particular token range should be EF43, and one of them is FF11. So FF11 gets voted off the island, and we know that we need to do some repair here. So the way that this works is that we walk the tree from from the root hash up, and we identified nodes that are the same across 2 different trees. And we can just ignore the entire subtree underneath that matching node and allow us to drill down to find the node or nodes that actually do differ. So in this particular situation, 999B is the same on both trees, so we ignore the left side. 4BBB is different than 3BC7, so we keep going until we find the individual node or the nodes that differ from one to the other. Then it's simply a matter of transmitting the bad nodes from one replica to the other. We rehash, and then the root hashes of the 2 Merkle trees are now the same. BitTorrent is also, BitTorrent as of BEP30 also uses a Merkle tree to authenticate pieces that you receive from untrusted sources to ensure that they actually are the data that you're looking for. And a little sketch of the protocol is Chester. Chester, the challenger, is searching for sweetwares.exe and gets a torrent file from a trusted source, which is the Pirate Bay. Everybody trusts the Pirate Bay. This torrent file includes the Merkle root for a Merkle tree created over the pieces for this file. So in this particular situation, Merkle hash is 63D5, and there are going to be 4 pieces. Pirate Bay and Chester agree upon the size of the pieces that are going to be used here. And then once Chester gets that torrent file, Chester will broadcast out to the universe that I want the first piece of wares.exe. And Patricia gets this, and Pedro gets this, and Paula gets this, and Pat gets this. And Pat is a jerk, so Pat says, I've got wares.exe piece 0, and here it is, and here's a proof that it exists in that structure. Or here's a proof that it exists in that file. And Pat is being naughty. Pat hates wares, so Pat sends a piece that's just a bunch of zeros. So Chester's in this situation now where Chester has not yet received any of the other pieces of data, any of the other blocks for this file, and needs some way to authenticate this piece of data. And all that Chester has is the Merkle root hash and the number of pieces. So how does this work? So Chester has the Merkle hash, the number of pieces, and an inclusion proof that was transmitted along with that data from Pat, naughty Pat. So Chester hashes this data. Everyone using one of these BitTorrent clients is going to agree upon the hashing algorithm to be used here. So we hash to CBDD, and then from the proof, the inclusion proof that Pat sent, we combine and hash, and then we compare Merkle roots. And in this particular situation, we can see that EF43 is not the same as the Merkle root in the torrent file, so we know this piece is actually bogus, unless somehow Pat has broken our hashing algorithm, which is unlikely. Storage, which is a company that will help you store files on the internet with untrusted folks, uses a Merkle tree to prove that someone is actually storing a file that they have contractually agreed to store. The way that this works, let's say that the client is the entity that wants someone to store a file for you, and the storage server is the entity that is contractually agreeing to store the file for the client. First, the client will shard their file. So we've got zenu.txt, it's a bunch of bytes. We're going to shard it into four shards. We choose a shard, and this is the thing that we're going to actually create a contract for. And we agree as part of our contract how many times the client is going to be able to challenge the entity storing the file to prove to them that they still have that thing. And this is negotiated up front. So the number of challenges that I pre-negotiate as the client, for each one of those challenges, I'm going to actually have to generate a salt. And I hold on to that salt, this mapping of salt index to this arbitrary, it's not arbitrary, it's actually fixed length number of bytes. And I'm going to first, before I transmit the data, I'm going to compute a Merkle tree over this data by prepending the salt onto the data for the shard. So in this particular situation, these red numbers here, you can just imagine that's the shard data. And I've only agreed ahead of time to challenge 3 times. So I'm going to create 3 different leaves here by hashing, double hashing that salt prepended onto the data. I'm going to hash these things all the way down to a Merkle root, and then I'm going to store that Merkle root along with the salts and the index for each salt. So I need to remember that S0 is in the first salt, S1 is the second salt, S2 is the third salt, and that the Merkle root is 63D5. Then I'm ready to engage in a contract with someone, and I'm able to send them the shard data along with the leaf set that I have computed over that data. So in this particular situation, by this point, the client has the Merkle root and stored the salts along with that index, and the storage vendor has the shard data and the Merkle leaves. So at some point in time in the future, the client wants to challenge the storage vendor to say, like, yo, like, do you still have this file, or did I just pay you to store that file and you threw it in the trash? So the storage vendor receives a challenge. The storage client chooses one of those salts and sends it. In this particular situation, it's going to be salt 0, and it's going to send it to the storage vendor. The storage vendor knows that it needs to prepend that salt onto the data for the shard that they received, and they compute the leaf. Then they look at the leaf set that they were already given as part of the contract negotiation process in order to determine which part of the tree this thing slots into. And once they identify, in this particular situation, that it slots in the leftmost node, if you draw trees this way, then it has enough information to send a Merkle proof that this thing actually exists in the tree. So the client receives the response, which says, this Merkle proof relates to salt 0 for a tree with root 63D5. And because it knows which salt was used, it knows how to apply this inclusion proof such that it actually computes the right Merkle hash. And if this hash is different, then that means that there's something wrong with the proofs, or the client didn't implement the protocol that they are contractually obligated to adhere to. It's a match. They win. So Merkle tree is just a data structure with tunable properties for space and inclusion proof size. It's used by lots of P2P projects. So get out there and experiment. It's part of Bitcoin. It's part of Ethereum. It's part of BitTorrent. It's part of storage, a bunch of different things, both in Cryptoland and also not, like you see with Cassandra DB and also with Git. So get out there and experiment. I've got some links such that you can get into the specifics of this data structure and also how they're implemented in different factor and the way that they balance trees and so on and so forth. So get in there and dig in. And if you want to look through a kind of crappy reference implementation, find me on GitHub. I'm Laser on GitHub. And there's a repo called Go Merkle Tree, which has got a pretty bare bones implementation. But actually, like, you can kind of figure out how they work just by looking at that. I posit. So that's it. Thank you very much for having me out.
Good job. Good job. Testing one. OK, there we go.
You're on.
All right, cool beans. So do we have any questions?
Just a comment. Is this on?
It is.
Okay. Yeah. If you're, well, I don't know what the hashing function you're using for the Merkle trees, but MD5 is broken, so it doesn't meet the 2 criterias for a cryptographic hash.
Mm-hmm.
And SHA-1 hasn't been broken, but something called a birthday attack.
Birthday attack?
Yeah. It's not recommended to be used for cryptographic purposes.
Mm-hmm. Yeah, thank you. Yeah, the many Merkle tree implementations that you'll find on the internet will allow you to plug your own hashing algorithm. And yeah, that's a good call out. MD5, probably not what you want to use. SHA-1, maybe not what you want to use, but there's some other things out there that you can plug.
All right. Do we have any other questions? Any other questions? Now, forever? Oh, okay.
Okay, so you went through the storage implementation pretty quick, and this is something that's kind of like, I've heard this before, and I'm still a little confused. It seems like if you're going to store challenges, you could just concatenate the challenge, your salt, with the data, and keep the hash of that. And like, so what does the Merkle tree really get you, aside from the fact that you only have to have a single, like the Merkle root, and not everything. Not
so
all the results.
let's look at this thing together. So you're the client here. Sorry, you're the storage vendor here. And so what's your question? You're saying like, why don't I just like compute a single hash over the
entire
over
file,
the data?
and then do that, or even just that one of those chunks, and then I mean, if you told I guess you could tell the vendor which chunk, and then like it just seems like rather than having to store store all the leaves, you can just store like twice as much data and get both, like have the salt and the result of a hash of that, and
Do you want to store
and have the same level of proof.
Well, like you definitely want to shard your data so you can distribute those shards across a bunch of different storage vendors. I doubt that you want to duplicate, as a storage vendor, like you want to duplicate like the amount of data that you have on disk. Like in this particular example, regardless of the number of challenges that the storage vendor and client like have pre-negotiated to exchange, the storage vendor only has to store one copy of the data, and for each challenge they prepend the salts.
Okay.
Yeah.
Might need a deeper discussion, but I think that's good enough.
Okay. Well, you can find me out. You know where I work.
I do.
Cool.
All right, do we have any more questions?
What kind of server do you think would be optimal for something that's dealing with all these hashing procedures like all the time? Would it be just like a big GPU cluster?
So for most of these examples, like these are P2P systems. So these are just like home computers that are computing these hashes. I don't know what kind of hardware would be particularly good at computing these kinds of hashes, but like as of that like Merkle extension for BitTorrent, for instance, like this stuff is just running on your regular computer, or anything that implements that particular part of the BitTorrent protocol is able to compute these things. What's up?
These hashing functions are precisely what all the ASICs for Bitcoin have been designed for. So it's like there's nothing memory hard about these problems. So like ASICs are the best hardware to like compute these things. And so Ethereum and some other cryptocurrencies have like come out with memory hard problems that require you to have some like amount of data available and in some kind of cache to like to make it so ASICs don't really work anymore. And then those are graphics cards.
There's if you want, I could spend 5 minutes and walk through a proof of storage problem that is like memory hard, but it will require a rather awkward change of presentations here. And notice when I said if you want, I didn't give you a chance to say no, because I get paid by the hour. So, all right. Dun, 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 dun. Spoiler, this thing I'm about to show is actually not a Merkle tree, but don't call me out. All right. The fabled Open Cmail Gateway, which is a company that doesn't exist. But you can imagine that Cmail uses a hash tree to prevent spamming. Can you imagine it? It really doesn't happen. But I'm going to talk to you about how it could happen. Okay, so Pedro, actor here, wants to send email through the Cmail API, and Cmail doesn't want its clients to use them to spam people. It just provides a service such that you can make an HTTP request into it and it will send email for you. So it forces the consumers to solve a puzzle in order to get an API token that can be exchanged for the right to send email through its API. The puzzle solution requires that a bunch of memory be locked up and cannot be discarded. And CMail will issue challenges periodically to Pedro to ensure that he's got that memory locked up, and will revoke his token if he no longer has that memory locked up. So protocol sketch, Pedro sends requests for an API key, and CMail responds with a puzzle. Pedro solves the puzzle. So Pedro has to have enough information to actually know what this puzzle is, and you're just going to have to make some assumptions about the way that this works. But Pedro solves the puzzle and then notifies CMail that Pedro is ready to respond to the challenge. CMail sends the challenge, Pedro responds with a solution, and then CMail will give him an API token with a TTL or something that will need to be refreshed periodically such that he proves that he still has that memory locked up. So the puzzle is, prove to me that you've allocated greater than equal to 128 bytes by creating a binary hash tree from a seed value, ABC4, using SHA-256. And what we know about the bit array that comes out of SHA-256 is that it will equal 128 bytes. So, and that's important for the way that this puzzle is designed. So Pedro has received this seed value. Pedro hashes using SHA-256, which produces a 32-byte bit array, or a 32-byte array. And then in order to lock up at least 128 bytes, we're going to actually have to produce a Merkle tree whose base is 4 leaves wide, because the hashing function that we're using is SHA-256. So starting from this hash value, if we go left, we hash the root, and then we append a byte and hash again. If we go to the right, we append another byte, and we hash again. And we do this all the way down until our leaf set takes up at least 128 bytes. An important thing to note here is that the directions that we move through this tree correspond to some binary numbers padded to log of the size of the base of the tree. So 0, 0 is going to be 0, 0, 1, 0, 2, and 1, 1 for 3. And that's going to be important when Pedro has to solve this puzzle. OK, so then the hashes, these leaves here, we store these things in a map where we are able to map the index of that hash to the hash itself. And an important property, once again, is that these keys are going to be 32 bytes. So in order to actually store this map, we're going to have locked up 128 bytes of storage. So then Pedro solves that puzzle. This is the puzzle solution here. Pedro notifies CMail that he has solved the puzzle and he's ready to respond to a challenge. And CMail needs to now prepare itself to send this challenge. So it has to create it. And an important property of this puzzle is that it needs to cause the prover to lock up memory in order to solve it. And then we don't want the challenger to have to lock up that much memory. So how do we do that? We start with the seed value. And because, OK, so sorry, let me back up. A thing that we are going to do is the challenge creation involves asking Pedro what the hash is of a certain index. And so what this guy needs to do, the CMail or the challenger, is actually figure out what that value is without actually computing the whole tree. So we take the index of 1, we convert it to that padded binary number, and we know exactly the hashes required to produce just that leaf. And we can map this hash directly to that index because of this property that I demonstrated earlier, the 1 and the 0. So yeah, right. So then the challenger will say, tell me the index of the leaf with this particular hash. And if Pedro has computed this map and has cached this thing, the lookup will be instant. If Pedro hasn't computed and cached this solution, we'll have to compute the entire tree at this point. It'll take some amount of time. And if we're clever, we can figure out if the amount of time it took him to compute that answer was slower than someone who had cached the solution. So that's kind of cool. Get your Merkle on. That's it. That's all I got.
All right. Good. Yep, keep going. All right. So I'm going to ask one more time, like, is there any other questions? No? Well, thank you all again for coming out, and I look forward to seeing you this Thursday for